Hey grade 12s, so we have just gone over double angles. Just to recap, there is one double angle for sine 2x, which can be replaced with 2 sine x cos x. We've got three options for cos 2x. We've got cos squared x minus sine squared x. We've got 2 cos squared x minus 1. And we've got 1 minus 2 sine squared x. So those four double angles are going to be used a lot with identities, with simplifying things. And you're going to, hopefully with practice, know when to use which one. Okay, I've already done 1.1 and 1.2 of exercise 2, so I'm going to hopefully mark up till the end of number 1 in this video. Okay, just to look at number 2 up to number 9, all using double angles and compound angles, so hopefully short little questions, you'd be able to get through most of them. Here we are in number 1.3. We are identities up to 1.9, 1.10 rather, and we need to prove that the left-hand side is equal to the right-hand side. So the way we're going to do it is we're going to focus on the left, we're going to work on the left-hand side, and hopefully we're going to equal the right-hand side. You'll see that I've written the right-hand side out in my little corner on the right-hand side, just to keep in mind as to what we're working towards. So in 1.3, we've been given sine x plus sine 2x over 1 plus cos x cos 2x, and hopefully tan x is what we're heading towards. So for the numerator, sine x plus sine 2x, we're going to change into 2 sine x cos x. It's the only option that it's got, over 1 plus cos x, and now we've got to decide. Cos 2x has got three options, right? So we're going to have to choose carefully as to which one we're going to use. I suggest we're going to have to use the 2 cos squared x minus 1, because then the denominator is entirely coses, and we can hopefully cancel accordingly. So looking at the numerator then, we could do what at the numerator? We could take out a sine x as an HCF, leaving us with 1 plus 2 cos x at the top. At the bottom, the 1 over there and the minus 1 would cancel each other out, and you could take out a cos x at the bottom, to be left with 1 plus 2 cos x at the bottom. Okay, agree with me? Happy? So we will see now that the brackets entirely can cancel each other out. That will be left with sine x over cos x, which we know to be equal to tan x, which we can now say is equal to our right-hand side over there. Awesome. Okay, 1.4. We are given the left-hand side of cos 5x plus sine 5x all squared, and we're hopefully going to get this right-hand side there, 1 plus sine 10x. Okay, so we're looking with slightly bigger numbers now. The first step would be obviously to FOIL this out. It obviously means that there are two of those brackets, so if I had to FOIL it out, I would get the F for FOIL, cos squared 5x. I would then get 2 of what? Cos 5x sine 5x, the O and the I of FOIL, plus sine squared of 5x. Awesome, there we go. So what do we know? That the cos squared 5x and the sine squared 5x together give you what? 1 plus 2 cos 5x sine 5x. Now think carefully. That is actually the expanded version of the sine 2x rule. But instead of an x, you've got a 5x. So watch here. I'm going to reverse back into sine of 2x, but not x. Sine 2 of 5x. Happy? So just on the right-hand side, just to show you how we usually do it, sine of 2 5x, how would we have expanded that? It would have been 2 sine 5x cos 5x. So we've just gone the opposite direction this time. And then we can just simplify. The 2 times the 5 gives us a 10x. We needn't even have the brackets, and that is indeed equal to the right-hand side. Happy face. Great. Number 5. Left-hand side equals cos 2 theta plus cos theta over sine 2 theta minus sine theta. And there's our right-hand side there that we're going to keep in mind. Looking at the top, do not be tempted to take out an HCF. Okay, there's nothing common there. You can't take out an HCF. We're going to have to change cos 2 theta somehow. Okay, how do you reckon we're going to change it? The numerator only has coses in it, Our right-hand side only has coses in the numerator, so I would change that cos 2 theta into a 2 cos squared theta minus 1. And then plus cos theta is over there. Sine 2 theta only has one option, so for us to change it into sine is 2 sine theta cos theta, and then minus sine theta is still there. Right, the numerator, if I had to reshuffle the numerator, and let's just go baby steps here, and bring the plus cos theta there, minus 1, over, okay, why by the way am I reshuffling it? Because in the next line, I'm going to hope to quadratic trinomial that numerator. The denominator, however, I can take out a HCF of sine theta. What would be left? 2 cos theta minus 1. Right, so there's my denominator, sine theta, 2 cos theta minus 1. So let's be careful. How are we going to quadratic trinomial the numerator? Firstly, it starts with 2 cos squared theta. So we're going to say 2 cos theta on that side and cos theta on that side. Let's just make this a bit bigger for you guys. Okay? Then how do we get to 1, 1, and 1? Now the signs have to be different, but together we have to have a plus cos theta. So we're going to see that this is going to be the minus and this is going to be the plus, which also works out conveniently because we can cancel the brackets entirely, leaving us with cos theta plus 1 over sine theta. Which was it? Yes, it was indeed equal there to our right hand side. Done. Okay, good stuff. 1.5 completed. 1.6 is an interesting one, and it's a difficult one. I remember the matrics from previous years didn't like it. They give you the left-hand side, which is very short and condensed, and here's the right-hand side we're heading towards. Okay, the left-hand side can be broken up using our double angles into what? 2 times 2a. Right, we've just learned double angles, so we might as well follow through with double angles. Using our double angle knowledge now, we've got 3 options, but looking at the right hand side, I would change this into 2 cos squared. Now what's our angle? 2a minus 1. All good? Then moving forward, I could now double angle again, right? In this case here, I've got what? I've got cos squared 2a, so I could change this here into what? Let's think carefully. I could say 2 of 2 cos squared a minus 1 all squared. You see that square over there is actually squaring the whole of my cos 2a. So quite awkward. Let me just write it up here as well. Cos squared 2a, forget the 2 in the front, is the same as cos 2a all squared. So now it's that cos 2a I'm writing as that, and I'm squaring it. And what's still on the outside? A minus 1. Great. Now we're going to do what with that square? We're going to have to FOIL out that bracket. It's 2 brackets, but we've just written 1. So baby steps, let's write it out twice. 2 cos squared a minus 1 and 2 cos squared a minus 1. On the outside, still a minus 1. 2 is going to hang in there for now. We're going to have 4 cos to the 4a. That's if I did the f of FOIL. Minus 2 cos squared a minus another 2 cos squared a plus 1. And outside there is the minus 1. Now you're going to see the magic happen here. 2 times the 4 is 8 cos to the 4a. Great, I've already got that part done. Those 2 together give you what together? Negative 4 cos squared a. You're minusing them together. So negative 4 when times by my 2 is negative 8 cos squared a. Great, I've got that. 2 times the 1 is plus 2, and then minus 1 that's been lurking on that side. So just to rewrite it all again, I've got everything I pretty much need now. The 2 minus 1 leaves us with the 1. Very tricky, I guess, equals to the right hand side over there. We've got it. Okay, so tread carefully through this. I know there is alternatives or a different way to do it. A thought would be that you could also say that cos 4a is actually cos of 2a plus 2a. And then you compound angle that and you double angle it, but hopefully you'll eventually get to the same answer. So a nice testing one there. 1.7, left-hand side is 1 plus sine 2x over sine x plus cos x. And they give you a hint, which they suppose they don't have to, is to change the 1. Okay, but before we get there, if I had to leave the 1 like it is for now, sine 2x is good to us because there's only one option, 2 sine x cos x over sine x plus cos x. Now, we'd be pretty stuck now. There's nothing else we could do now. But if you keep the right-hand side in mind, there's going to be some cancelling that we need to do, some cancelling. So, when we say change the 1, we are going to change the 1 into a sine squared plus cos squared x. Now, why did I put the cos squared over there? Because in the middle, I'm going to have this term of 2 sine x cos x over sine x plus cos x. Now, what am I going to do with the numerator? Denominator is fine, got no issues there. But the numerator, I'm actually going to quadratic trinomial it. So I'm going to start both brackets with a sine x. I'm going to end both brackets with a cos x. And sines are going to have to be what? Because I've got a middle term of 2 sine x cos x, both signs will have to be positives. I can now cancel one of the brackets with the denominator, leaving us with sine x plus cos x, which good for us is equal to the right-hand side over there. Okay, so if you find yourself hitting a bit of a dead end, often changing a 1 is the way to go. 1.8, left-hand side is cos theta over sine theta minus tan theta. Also a tricky little question, and you'll see why. Initially, is there much I can do? Not too much. Cos theta over sine theta we'll just leave here for now, and tan theta can be written as sine theta over cos theta. Now, if I wanted to find an LCD, because I'm subtracting fractions, I need an LCD. Sine theta cos theta would be my LCD. My numerators would be cos squared theta, right, minus sine squared theta. Now, please don't say that that is 1, because it's totally not. That is actually what? The cos 2 theta double angle. And we are over sine theta cos theta. Can I cancel the causes? Can I cancel that cos with one of the tops? No, never ever. You can never do that. What we're going to have to do now, because our hands are tied and we're nowhere near looking like our right-hand side, is I'm going to times this by 1, but not by 1. I'm going to times it by 2 over 2, which is actually 1. And why do you think I do it that way? Because if I times it by 2 over 2, I'm going to create 2 sine theta cos theta at the bottom, which we know is going to be what? Not there. It's going to be a sine 2 theta. And if I've done it at the bottom, I must also say 2 cos 2 theta. 2 cos 2 theta. What is sine over cos? Sine over cos is tan. So if this is like the upside down version of it, where is the tan going to go? Tan of 2 theta is going to appear at the bottom, and what's still stuck at the top? The 2. And are we equal to the right-hand side? Yes, we equal to the right-hand side. So be aware of this little trick over there. In order to create a double angle, I've times by 2 over 2, which isn't really changing the question. It's in essence timesing by 1, but it's enabled us to get to the answer. Right, the last two. Left-hand side of 1.9, sine x plus cos x all squared. We know pretty much what we're going to have to do. We're going to FOIL that out because there are two brackets. Sine squared x plus 2 sine x cos x plus cos squared x is the FOIL. We are then going to be able to say that plus that together give you 1 plus 2 sine x cos x. And what is 2 sine x cos x? It is the expanded version of sine 2x, which now makes us equal to our right-hand side. Easier one after a difficult 1.8. 1.10. Oh, this one looks fun, and I hope it's going to be understandable to you. Right, I have chosen to say, let's work with the right-hand side and hopefully get equal to the left-hand side in the end. Why? Because the left-hand side only had a sine x plus a cos x. There was nothing really I could do. Looking at the right-hand side, though, you've got root 2 cos of 45 minus x. What are we going to do? There was an example a few pages ago that's helped you think in terms of graphs. If I had to take out, right? Well, let's go baby steps here. If I leave the root 2 for now, and I'm going to now use my, I forgot the word, compound angles to expand this, what would it look like? Cos 45, cos x, plus sine 45, sine x. Do you remember? Now, we are going to have the root 2 still there. Cos 45 can be written as root 2 over 2, special triangles, and cos x. Sine 45 can also be written as root 2 over 2, and we've got sine x. Lastly, we're going to times this into the two terms. Root 2 times in, we would get what? Root 2 times root 2 is going to give us 2. Over 2 is going to give us 1. So that is going to cancel out there, and we're just going to have what left? Cos x. Same thing when I times this root 2 in over there. We're going to cancel with the root 2 over 2, and we're just going to have a sine x left. To make it look exactly like the left-hand side, I guess we could rearrange it, equals the left-hand flippin' side. Right, a bit of a toughie, but hopefully you understand number ones. Continue with exercise 2, please. It goes on to number 2 that talks about general form or general solutions. Number 3 talks about the maximum value of things. Let me just go up here in case you don't have your notes. So the general form, the values for it being undefined. So the denominator, remember, denominator would equal 0. Right, the maximum value, so you're going to think of your graphs. Evaluate without the use of a calculator. We're going to break that up, double angles or possibly compound angles. If tan 25 is m, remember those ones, 25, 90 degrees. Tan is opposite over adjacent, so m over 1. We can work this out to be whatever. Okay, remember that for number 5. Number 6, 7, 8, also similar kind of things. And number 9, they end off with a triangle and they ask you to prove something. Hopefully that's given you enough to work on in terms of double angles. I'll make one more video on exercise 2.